So now I'm trying to convince you that in some cases this allows us to have simpler analysis. So what usually, the typical proofs in rigidity theory is just to look at this Jacobian matrix and somehow compute its rank, understand what the rank is. So here I'm avoiding this list, computing the rank of matrices. So here is the claim. So I'm not going to really give all the details of the proof. It will be more sketch, but you'll see the idea. So one claim. So 0 and 1 extensions preserve rigidity. Okay, so here's the sketch. So we're going to prove this by induction on the number of vertices n. Okay, so suppose we start with a graph G prime of n minus 1 vertices, and we know that this graph is rigid. Okay, so by the induction hypothesis, we know that this variety x of G prime is of dimension 2 times n minus 1 plus 3. And now we want to know that when we apply a 0 extension or 1 extension, then the dimension is at most 2n plus 3. Okay, so let's start with 0 extension. So remind you what it means. It means that we just add a vertex. So we have a graph, G prime, and we add one new vertex of degree 2. So how does it look in terms of the lines? It means that we need to add a new line for this vertex. And this line will need to intersect two other lines, because it is connected to two other vertices. So we look at so the idea is we look at configurations that realize the graph G prime, and then these two vertices are just some pair of lines, and we need a new line to intersect these two lines. So we have exactly two new degrees of freedom. You can choose a point here, and this will determine the line. So we had new 2 degrees of freedom, so the total degrees of freedom that we have, so total number of degrees of freedom is, so this is 2n, 2 plus 1 plus 3 plus 2 is exactly 2n plus 1, which is what we need. Okay? So of course, this is not a formal proof, but it can be very easy. Proof, and for one extension, so again, we start with a graph G prime, n minus 1 vertices. And now we have this graph G prime, and it has 3 vertices u, v, and w, and we want to add a new vertex z connected to these 3 vertices and remove this edge. Okay? So what should we do? So let's first of all remove the edge uv, look at the variety that corresponds to, remove uv, and look at x. So this is g double prime. Okay? So now we started, so we know that x G prime has dimension as here, 2 times n minus 1 plus 3. Okay? And now we removed an edge. So we can reduce since we already see, we can reduce the dimension only by at most 1. So the dimension, so this is 2n plus, sorry, we can increase the dimension. So this is 2n plus 1, so the new variety x G prime plus, so the dimension of this is either 2n plus, it is at most 2n plus 2. Okay, so more precisely, it is either this or 2n plus 1. Okay, so we have this variety, and now we need to add this vertex. So what does it mean to add this vertex in terms of the line configurations? So we just need to take a new line, z, which will intersect some existing 3 lines, u, v, and w. Okay? So this is what we want to do. So let's look at these 3 lines. line corresponds to U, line corresponds to W. If, for example, they are skew, so the pairwise non-intersecting, then how many degrees of freedom I will have for the new line, let's see. So it will be exactly 1 degree of freedom. It will have to lie on error. So in this case, we will have 1 degree of freedom, and one can check that whenever, except for the 2 cases where the 3 lines, LU, LV, and LW are concurrent or coplanar, we will always have at most 1 additional degree of freedom. Okay? So if they are not concurrent or coplanar, we had only 1 degree of freedom, which means that now we will have, so it's at most 2n plus 2, plus this 1 degree of freedom, and this is 2n plus 3. Okay? But there are these 2 cases where we can, where this new line might add 2 new degrees of freedom, and then it will be too much if we're in this case. But so do you see why we're not in? Why this is not a problem? So it's not a problem because if the 3 lines are concurrent, it means that actually we have this edge UV that we, so we didn't really remove this edge UV because they intersect. So it means that this distance is still preserved, or the 2 lines still intersect. So if they are concurrent, it means that actually x of g prime is contained, x of g double prime is contained in x g prime. And then the dimension is, and then we're in this case, the dimension is 2n plus 1. And then adding these 2 degrees of freedom again yields was 2n plus 3 degrees of freedom. Okay, so this is for this statement, but so probably I don't have time, but the same way, and very easily one can reprove the result of quadratic. Okay, so this is one thing I wanted to say. And another thing that I find, so when should I stop?
I think we have the room till 5:30, right? So you have 5 more minutes.
So it's okay. No, it's okay. So I won't show the proof about the global rigidity, but it's really similar to this one. And so another thing I wanted to say here is, okay, so we get this characterization of rigidity in terms of these varieties, but the thing is that these varieties can correspond to other variants of the original rigidity problem. So for example, if we look at points on the sphere, we can ask the same question. We have points, we fix the distances here, and we ask whether it is rigid, the most natural analog to the question, right? So it turns out that also for points in the sphere, we can associate rigid motions of the sphere. And again, for a pair of points P and P prime, we can look at all the rigid motions that takes P to P prime, and then again interpret this problem as a problem about line configuration. So this result actually shows that all the result about rigidity in the plane, they go immediately. They just translate it immediately to the question about rigidity on the sphere. So this was known. It was known that rigid graphs embedded to the sphere has the same characterization as in the plane. But here we just get it immediately because we can look at transformation here. And also, if we replace, so if we look at the problem of rigidity, but instead of fixing the distances on the edge, we fix the slope. Okay. So again, this question, again, we can look at transformations that take P to P prime and preserve slopes in the plane. And then we again can use this result and get the same characterization. So all the characterization of rigidity in the plane translates in straightforward way to, or are generalized to the case of slopes instead of distances. So again, it was known, but it was like a separate work, and now we get it for free from the analysis of the lines. And maybe a third thing that I want to say is, so Another thing that we can see from these line configurations is, for example, so there is a result of Goods and Cuts that says that if, so it's relatively new and it's a deep result, and what it says is that if we have n lines in R3 and the number of pairs of lines that intersect is more than square root of n times log n times a constant, then there must be at least square root of n lines that lie on a common plane or concurrent or on common regulus. Okay? And this immediately tells us something about configurations of points. So if we have a graph with more than this number of edges, and we look at two realizations of this graph, then we know that there's always a subset of size square root of n of vertices that is congruent to another subset, unless they are on a regulus. But if they are on a regulus, then it means that the points lie on a conic section. So still we have a very clear picture of what's going on. Okay, so I think I'll stop.
Any questions?
For graph rigidity, is there any minor forbidden property with respect to extension?
So you mean if the graph does not contain this
Because
minor, then it is
extension, it just gives me the sense of like creating graphs from the property of minor forbidden.
right. So I know about this characterization with like building it with 0 extensions or 1 extension, but I don't know anything about the minor. So I think that there is no, but I don't know much more.
Any other questions?
Yeah, quick question. Are there any rigidity statement for embeddings in space where you actually have surfaces that you want to preserve as opposed to just length of edges?
So what do you mean by preserving surfaces? Like the area? Or?
Yes, area.
So I think, so actually I'm not really an expert to the rigidity results here. I only ran into it because of this thing with the line configuration. But there are things like that, but I'm not sure. I cannot.
I see. So there's no line configuration mapping for these versions?
So not that I can think of. This is really the special.
So,
So whenever I see this construction, so somehow you are always taking some affine patch from the Grassmannian, right? By throwing it away. So is there some way to express all this projectively in sort of the language that the algebraic geometers would be happy about?
So you can look at this. So what do you mean? I mean, you can look at these varieties in the projective complex. What do you mean by expressing?
Like, for example, you took the horizontal lines, right? So that means in the Grassmannian you're throwing away something.
Right, so I think
So
this is not necessary. You could take
you
the.
could, do
And
this.
that, because it's the same, if lines intersect, if they are parallel, then it means that there is a translation that takes one. So I think everything will work if you extend it there.
Any other questions? Well, let's thank Orit again.